In this module, I would like to introduce this module, graph algorithm, NP completeness, and intractability, linear programming, and approximation algorithm. And we want to emphasize the overview and the agenda of this module. You may find out the title of this module is quite long, and we think that it's really good to put them together. The reason they are related. Let's see. First, let's briefly see why we needed to have graph algorithm, right? So a data structure is a data connection and its manipulation that are used to manage objects and object relationship in the connection. A proper choice of data structures can greatly facilitate elegant algorithm design and reduce the running time of this algorithm. For example, parallel heaps, right? So far, we have dealt only with linear structures and trees. Typical linear structures are lists, queues, and stacks. A linear structure can be considered a special case of a tree, where every node except for a single leaf has exactly one child. Just as trees generalize a linear structure, graph generalize trees. The key difference between trees and graphs is that in a graph there may be more than one path between two nodes. In other words, graphs can contain cycles, right? But the trees disallow that. Graphs are very useful and important data structures with wide applications. Many real-life complex data can be elegantly managed as graphs. For example, social network. An incredible variety of computational problems can be phrased in terms of graphs. For example, how to find most influential people for an advertisement company through social network data, Facebook data, Twitter data. For example, this is a question people ask you. People want you to find a solution for them. The people want you to find efficient solution. In the module, we begin with our discussion of graph terminology, representations. Both topics will put in another video, not a single video. Then we will talk about graph traversal, corresponding to how to walk through a graph and discover all objects and objects relationship in a graph, following with several other popular graph algorithms. For example, finding a minimum spanning tree. With complex data structures and corresponding algorithms being introduced, we would study from the theory of computation and answer the long-rooted question. Can all the problems be solved in polynomial time? And if that is linear data structure, since it's easy, and once a complex data structure is in this graph structure, and we want to convince the people what the solution we have could be the best. We also want to convince the people if they give us one problem, if we claim there's no polynomial runtime, low efficient solution could be. In that case, we also want to prove to them that's true and there is no efficient solution for a specific computational problem. And in this module, we want to learn which type of computational problem belong to that tractable group or belong to intractable group. Most algorithms we have studied have been polynomial time algorithm. On inputs of size n, the worst case running time is O n to the power of k for some constant k. But not all the problems can be solved in polynomial time. For example, Turing famous halting problem cannot be solved by any computer, no matter how much time we allow, which is known as NP hard problems. There are also problems that can be solved but not in time or n to the power of k for any constant k. Namely, no polynomial time algorithm has yet been discovered for an NP-complete problem. Nor has anyone yet been able to prove that no polynomial time algorithm can exist for it. A problem with a polynomial algorithm is tractable, and problems that require super polynomial time as being intractable or hard. The list of problems who belong to NP-complete and NP-hard classes. And for such a class of problems, we could use linear programming or approximation algorithm to solve them and retrieve approximate solution. In that case, we cannot get the optimal solution, but we can get some solution very close to optimal. And this is the reason we packed all these topics together. And we wanted to take a look at advanced data structure graphs. And we want to check typical algorithm in the graphs. And we also want to check on the graph or any kind of problem. It could be intractable or tractable. If it's intractable, we want to solve through the linear programming or approximation algorithm. By the end of this module, students will be able to demonstrate understanding of different graph representation, different traverse algorithm, and different typical algorithms, distinguish classes of PNP, NP-complete, and NP-hard problem. We'll give you some examples. We just need to focus on these examples. You do not need to have exhaustive search for that. And demonstrate understanding of linear programming. And we will give you some examples for typical NP-complete problems, and which is based on the graph vertex covering, maximum graph matching, or assignment problem. And the materials we will also give to you. I think that's all for this video, overview and agenda. Although we have very short discussion about the agenda, right? In the agenda, we want you to follow the steps. And these steps is here. It just reminded me, I would like to give you a little bit explanation for that. The agenda, this is the, oh, I think okay, let me change that. In this agenda, I would like you take a look each specific concept. We have 7 concepts, and usually this two together may take 1 hour, and this one minimum spanning tree maybe take 2 hours. This one 2 hours, and each this one take if you use a video, it will take 1.5 hour, and this together this will be very short concept, and maybe take half hour. This take 2 hours, and after that we have the quiz. We have several quiz posted in each sub question, each sub concepts. So once you finish this concept, you take a quiz, and usually we want it to open in the different browser tab, and take a look at each concept and then go to check the questions. I think in the total we may expect you spend at least 8 hours for all these concepts, and then we'll have another assignment, and which is based on to see how to use these concepts. And I think I think this one, that's it. Okay, so I think that's all for this video.